Hello everyone, in today's video we'll be doing part 1 of a part 1 and part 2 series for the history of physics. Physics is a phenomenon in science with properties of energy and matter. They can relate to volume, mass, mechanics, heat, radiation, structure of particles, etc. Particles make up everything, which include molecules, atoms, protons, electrons or photons, just to name a few. You may also notice that this is the first voiceover, as I intend to try and do this as a new deliverable method. Without further ado, let's get right into it. Thales of Miletus postulates that water is the primary substance of Earth. He was also acquainted with the attractive power of magnets and rubbed amber. Thales was a physician who discovered everything is a form of water, or everything breaks down into water. The important context in Thales' hypothesis was that not everything is physical liquid, as many objects and substances are dry. As Thales' hypothesis is somewhat confusing, with everything being water, he means it was an observation that nature and the nature of all things is moist. As a result, Thales believes that it is water, which means it is the matter of everything, this being known as material monism. Pythagorean is best known for the field of mathematics for his famous equation dealing with right triangles. A2 plus B2 equals C2, which is known as the Pythagorean theorem. However, Pythagorean was also known for spherical volumes. Around 520 to 500 BC, ancient Greece started to believe that the Earth was round and not flat. Pythagorean first proposed a spherical Earth, mainly on aesthetic grounds rather than any physical evidence. Like many Greeks, he believed the sphere was the most perfect shape. The first person to really propose a spherical Earth with physical evidence was Aristotle, who listed several arguments for a spherical Earth. He proposed the Earth casts a round shadow on the Moon during a lunar eclipse, and different constellations are visible at different latitudes. Around this time, Greek philosophers had begun to believe that the world could be explained by natural processes rather than invoking the gods, and early astronomers believed making physical measurements in part to better predict the seasons. The first person to determine the size was Eratosthenes, who produced a surprisingly good measurement using a simple scheme that combined geometrical calculations with physical observations. Aristotle's research on physics is now covered by physics, biology, and other natural sciences. His terminology, natural philosophy, is an affiliation in conjunction with the natural world. This was known as the 5 elements of nature, which are earth, water, fire, air, and space. All those elements are interrelated to his other concepts of motion. Natural motion depends on the element concerned. The ether naturally moves in a circle around the heavens, while the 4 Empedoclean elements move vertically up like fire, as is observed, or down like earth towards their natural resting places. In physics, Aristotle believes that objects fall at a speed proportional to their mass and conversely proportional to their density of the fluid they are immersed in. This is a correct approximation for the objects in Earth's gravitational field moving in air or water. There have been divided opinions over many centuries whether Aristotle intended to state qualitative laws. Author Henri Cateron, for example, was a firm believer in Aristotle's theory being qualitative, but many others debunked this. Cosmology, theorized by Aristarchus of Samos, was proposed in a similar way 2,000 years later by Nicolaus Copernicus. However, the great prestige of Aristotle and Aristarchus' heliocentric model was rejected in favor of the geocentric model. This meant that everyone against their proposals believed every other celestial object in the solar system revolved around the Earth instead of the Sun. Aristarchus determined the sizes of the Sun and the Moon as compared to the Earth's size. He also estimated the distances from the Earth to the Sun and Moon. He, along with Aristotle, are considered one of the greatest astronomers and physicians before Common Era. At the time, their theories only remained debatable and polarizing conjectures. Archimedes was a great pioneer in theoretical physics. He was well known for discovering the foundations of hydrostatics and mechanics and laws of levies and pulleys. The principles of hydrostatics are disciplines of fluid mechanics that investigates the concept of the equilibrium of a floating body and submerged body fluids at hydrostatic equilibrium. Therefore, his publication theorem was pressure in a fluid or exerted by a fluid on an immersed body, as opposed to fluid dynamics and the study of fluids in real time. More related to our topic of physics, the discovery of the laws of levers and pulleys are in conjunction with having the ability to have more heavy objects using small forces. They utilize the laws of physics efficiently to move weight over distance. This allows one single person to move mass better than a human would be incapable of lifting without the intervention of such tools. Levers, for example, functions in identical principles relating to Archimedes' law, but in a completely different physical manner. If you take a 10-foot board and rest it on a fulcrum at its center, this makes it possible to place the mass on one end and lift it by pressing down on the other end. A distance that is lowered on one end will be identical to the distance that the other end lifts you, will require the same amount of mass. However, if you counterbalance the axis from the center of the board, the lever you would gain a mechanical advantage. If the fulcrum is 1 foot from one end and 9 feet from the other end, this makes lifting an object more broadly high and mass by simply lowering the long end 9 times farther than the shorter end rises. The overall legacy of pulleys and levers that operate in the same principles of physics theorized by Archimedes constitutes the basis for many modern machines. Everything from water wheels to internal combustion engines that utilizes the principles of transforming mass into distance. Claudius Ptolemy collected the optical knowledge at the time. He also invented a complex theory of planetary motion. Ptolemy's work commissioned astronomers and physicians to make credible predictions of planetary positions, solar and lunar eclipses. Ptolemy was convinced by Aristotle's postulation that the sun and planets revolved around a spherical Earth. He believed this by developing a piece by observing them in mathematical detail. By doing this, he repudiated Aristarchus' theory of the Earth revolving around the sun. At the same time, Aristarchus has provided no evidence to back up his claims at the time, which is why his theory lacked credibility. Ptolemy saw the universe as a set of nested transparent spheres, with Earth in the center. He hypothesized that the Moon, Mercury, Venus, and the Sun all revolved around the Earth. Beyond the Sun, he believed Mars, Jupiter, and Saturn the only planets known at the time, as they were visible to the naked eye. Beyond Saturn lay a final sphere with all the stars fixed to it that revolved around other spherical objects. Ptolemy later deduced the fact that every size, mass, motion, volume, and brightness of planets varied. He then subsumed Hipparchus' theorem of epicycles, put forth some centuries later, to work out his calculations. Epicycles were small circular orbits around imaginary centers on which the planets were said to move while making a revolution around the Earth. By using Ptolemy's tables, astronomers could accurately predict eclipses and the positions of the planets, because real visible events in the sky seemed to confirm the truth of Ptolemy's views. His ideas were accepted for centuries until the Polish astronomer Copernicus proposed in 1543 that the Sun rather than the Earth belonged in the center, whom we will discuss very shortly in the video. Between the years of 1011 to 1021, Alhazen published his 7 books on optics. Volume 1 deals with Alhazen's theories of light, color, and vision. The second volume is where Alhazen presents the theory of visual perception. Both volumes 3 and 6 present Alhazen's perspective on the errors in visual perception, with volume 6 which focuses on errors relating to reflection. Both volumes 4 and 5 provide experimental evidence for all Alhazen's theories on reflection. Lastly, volume 7 deals with the concept of refraction more broadly. The 7 books on optics was one of the most influential books in the history of physics, as it is widely considered initiated a revolution in the fields of optics of optical revolution. The 7 books also had an important insight on the development of optics, as it laid the foundations for modern physical optics after radically changing the way light and vision had been perceived, and on science in general with its introduction of the experimental scientific method. Alhazen has been called the father of modern optics, the pioneer of modern scientific method, and the founder of experimental physics, and for these reasons he has been described as the first scientist. During the 13th century, Roger Bacon can be seen as having among the first scholars to emphasize the physical relevance of mathematics. His rationale for reinforcing the physical relevance of mathematics has epistemic philosophical elements, but also has metaphysical elements which have to do with the way in which Bacon conceived the structure of the physical world. Everything that exists in nature was brought into existence by 2 causes, the efficient and the material cause. To understand physical agency brought about efficient causes requires mathematics, because physical operations occur by means of forces like light, which operates through rays, which was touched on from the 7 books of optics. Not only physical agency, but psychic and astrological agency require mathematics as well to understand. For Bacon, light is an instance of physical agency through forces, following the geometrical rules of reflection and refraction. It is a privileged case of such agency because of its visibility. Here also lay the reason why science, light and vision perspective is embedded in the theory of the multiplication of science. If a natural philosopher wants to explain natural processes, they must focus on the lines of physical action and employ mathematical methods. Natural philosophy must follow the principle of motion and rest, which involves instances of change, and science following geometrical principles. He taught that in order to learn the secret of nature, we must observe. He thus provided the method by which people can develop deductive theories using evidence from the natural world. Nicolaus Copernicus, one of the most well-known astronomers during the Renaissance era, disputed the geocentric planetary theory proposed during the Antiquity period and published his belief of the heliocentric planetary theory, which is again where planets revolve around the sun. At the time, the terms astrologer, astronomer, and mathematician were used interchangeably. They generally identified anyone who studied the heavens using mathematical techniques. Nevertheless, he published his thesis sometime between 1510 to 1514, which was known as the Commentariolis, or Little Commentary, which was a new cosmological theory of the heliocentric universe and published many copies to various astronomers, scientists, and physicians. It thus became Copernicus's contemporaries, although it was never physically printed during his lifetime. There were copies, however, printed after his death, as it subsequently lapsed into obscurity, and its previous existence remained known only unofficially until a surviving manuscript was discovered and published in the second half later in the 19th century. One of the most significant years of Copernicus's life was in 1543, which is when the Copernican heliocentralism was officially established. The geocentric model by Ptolemy was overruled and replaced by Copernicus's heliocentric model unanimously. The geocentric model has been prevailed for centuries, which had placed the Earth at the center of the universe, thus every planet orbiting Earth. This was achieved by Copernicus by presenting a feasible theory more elegantly and accurately, determining the length of a solar year while preserving the metaphysical implications of a mathematically ordered cosmos. Copernican heliocentrism preserved many of Ptolemy's elements, causing a number of flaws such as the planet's circular orbits, epicycles, and uniform speeds. At the same time, ideas such as the Earth being one of several planets revolving around a stationary sun in a determined order, the Earth having 3 months daily rotation, annual revolution, and annual tilting of its axis, which is how we form our yearly seasons. Retrograde motion of the planets explained by the Earth's motion, and the distance from the Earth to the Sun being small compared to the distance from the Sun to the stars. All those ideas were used at the same time by Copernicus contesting against Ptolemy's theory. Copernicus later died in the year of 1543 after he recently established his official astronomical model. There were many celestial objects and general discoveries done in the early 17th century by Galileo. He is considered by many to be the father of modern physics because of his willingness to replace old assumptions in favor of new scientifically deduced theories. With the endeavor to keep practicing, his invention of the 3-powered spyglass from lenses were sold in spectacle maker shops. He quickly figured out how to improve the instrument after he taught himself the right way to use a lens by grinding and inventing an increasingly powerful telescope. In August of 1609, he presented an 8-powered instrument to the Venetian Senate. Later in that year, he drew the moon's phases seen through the telescope, showing that the moon's surface was rough and uneven. In the early months of 1610, he discovered the 4 moons orbiting Jupiter in the Jovian system, which were Ganymede, Europa, Callisto, and Io. He also discovered that Saturn has rings. This was his first and major astronomical discovery. At the time, most people believed that the moon was a smooth sphere, but Galileo discovered that the moon has mountains, pits, and other features just like Earth. Galileo studied Venus and was able to say and conclude with concrete evidence that the planets orbit the Sun and not the Earth, as this was in mainstream astronomical education, and at the time, and has been for many years. Moreover, Galileo used his telescope to learn more about the Sun. There was little to no knowledge about the Sun's true luminosity, which compromised Galileo's eyesight. As we all know, looking into the Sun with your eye is dangerous. Galileo discovered that the Sun has spots which appear to be dark colour in conjunction with looking at the Sun. His work was laid for the foundation of today's modern space and telescopes. Tycho Brahe and Johannes Kepler were both physicians who worked together. Brahe's occupation was improving astronomical observations with new instruments like quadrants and sextants. This is how the 1 minute of arc was measured, which was a major contribution to better quality telescopes with more accurate dimensions and angles. Attis' quadrant plane of geometric theory was measured at 160 degrees, which equals 0.16 degrees, with arc seconds of 60, and the following radians and milliradians were all equal to 60. This is essentially how the measurement of a minute or other units of time were officially defined. kind. Kepler was a German mathematician, astronomer, and physician who again was a mentee of Brahe. He continued Brahe's observations and used the notes of his senior to develop the laws of planetary motion. Brahe's accurate celestial data allowed Kepler to develop his theory of elliptical planetary motion and provide evidence for the Copernican system. In addition, Kepler writes a qualitative description of gravitation. Both their contributions were essential to understanding the universe. Brahe's studies were valid enough for Kepler to discover other planets that moved in elliptic orbits, and his other laws, which gave Isaac Newton, who we will talk about next, the clues needed to establish the universal inverse square gravitation. Kepler was an extreme believer of the Copernican heliocentrism and found that the notion of Ptolemy's theory absurd and impossible as they contradict the laws of planetary motion. Kepler's laws of planetary motion have three components, which how they move in elliptic orbits, with the sun or parent star as a focus, a planet covering the same area of space in the same amount of time no matter where it is in the orbit, and a planet's orbital is proportional to the size of its orbit of an axis. If Ptolemy's theory was hypothetically true, then no planet or other celestial object in our solar system would have enough mass or density to maintain any of those three laws of planetary motion. Many of us know Isaac Newton, who was the man who saw the apple fall from the tree, which inspired him to invent the theory of gravity. Of course, that didn't happen, as it was just a myth. The apple was a figurative symbol for gravity. His gravity theory was likely inspired by Kepler's laws of motion. Newton used his mathematical description of gravity to derive Kepler's laws of planetary motion, account for tides, the trajectories of comets, the precession of the equinoxes, and other phenomena, quashing all doubts about the solar system's heliocentricity. Moreover, Newton's mathematical approach has become so basic to all the physical spectrum that he is dubbed as the father of the clockwork universe. Newton was known for many accomplishments that we all know today. As some of us may take calculus for granted today, we forget the fact that Isaac Newton created this mathematical concept when he was only 24 in 1665. It is used in all fields of science, including physics, biology, economics, chemistry, pure mathematics, and every aspect of engineering, just to name a few. Newton later became involved in a dispute with Gottfried Wilhelm Leibniz over priority in development of calculus. Most modern historians believe that Newton and Leibniz developed calculus independently, but with completely different mathematical notations. Some people see it as Newton publishing nothing about it until 1693, and did not give full account until 1704. Leibniz began publishing a full account of his methods in 1684. Leibniz's notation and differential method is now seen as more convenient notations, which were developed by continental European mathematicians in the early 19th century. In 1666, Newton observed the colour spectrum existing in a prism in the position of minimum deviation, where the ray is entering the prism in a circular motion. This led him to conclude that colour is a property intrinsec to light, a point which had until then been a matter of debate. When he published his optics theory during the early 1670s, he investigated the refraction of light, demonstrating that multicolored image produced by a prism, which he named a spectrum, establishes the colored light does not change its properties by separating out a colored beam and shining it on various objects, regardless of whether reflected, scattered, or transmitted. The light will always remain the same color regardless of any circumstance. It was observed that color is the result of objects interacting with already colored light rather than objects generating the color themselves. This was known as Newton's theory of color. Lastly, his most popular piece of work is gravity. He spent between the years of 1679 to 1687 researching gravitation and the effect of orbits on the planets in reference to Kepler's laws of planetary motion. Newton's broad interest in astronomical matters grew further, particularly when the great comet of 1680 flew past Earth, on which he corresponded with John Flamsteed, which gave him more pleasure in his gravitational research. The Principia, or the Laws of Gravity, was later published on July 5, 1687. These laws describe the relationship between any object, the forces acting upon, and the resulting motion, laying the foundation of classical mechanics. Any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. The principle of interference of light was established by Thomas Young. as he renewed the study of the century-old wave theory of light. Considering some of Newton's experiments, Young came up with the concept for the now famous double-slit experiment to demonstrate the interference of light waves. The demonstration would provide solid evidence that light was a wave, not a particle. He also used the data to calculate the wavelengths of different colours of light coming very close to modern values. He was the first to describe astigmatism in 1801, which was the same year he turned to the study of light. By allowing light to pass through closely to set pinholes onto a screen, Young found that the light beams spread apart and overlapped, and in the area of overlap, bands of bright light altered the bands of darkness. With this demonstration of the interference of light, Young definitively established the wave nature of light. He used his new wave theory of light to explain the colours of thin films, such as soap bubbles, and relating to colour wavelength. He calculated the approximate wavelengths of the 7 colours recognised by Newton. In 1817, he proposed that light waves were transverse, vibrating at right angles to the direction of travel, rather than longitudinal waves, vibrating in the direction of travel, as had been assumed, and thus explained polarization, the alignment of light waves to vibrate in the same plane. Young published the problem of color perception, and proposed that there is no need for a separate mechanism in the eye for every color. If you watched all the way to the end, thank you for listening, and stay tuned for part 2 coming in the very near future, as we will discuss more of modern physics. There was quite a bit to get through, which is why I decided to split these into 2 separate parts. Let me know in the comments section whether you prefer voiceovers or slideshow videos. Thanks again, and see you in the next video.